Hello and welcome to this uTasker Shorts video in which we'll be looking at connecting a simple keyboard or a keypad to a Kinetis KL82. Working with the uTasker project in Visual Studio, I've already configured the target in config.h for the KL82. Now I move to the area of the configuration which is responsible for the keyboard. This is it, called Support Key Scan, and for the Freedom KL82Z board I've defined a virtual keypad with 12 virtual rows and just one virtual key column. The reason why I do this is because the code supports auto matrix keypads, and if I set a column of 0, this means that we are actually using just a row, but we're making it look like a matrix. Here we can see the circuit diagram. We have 12 buttons. Each of the button is grounded at one side and then is connected to the processor on an individual port input. The processor will have a pull-up connected so that it reads a 1 when there's no button being pressed, and it reads a 0 when a button has been pressed. These are the ports which we need to connect to. For example, port C bit 5, port A bit 4, etc. When the key scan operation is enabled in the project, we have the opportunity of initializing these pins in the init key scan macro. And in application hardware Kinetis, I've added these connections. As we can see, each of the individual key connections is defined to the port which they're going to be connected to, and the initialization routine itself configures each of these as inputs with enabled pull-ups. The next thing to be aware of is that the configuration of the tasks in the project now includes a key polling task. This is polling, for example, at a rate of 50 milliseconds. Now, in order to get a quick overview, I'm going to let the project run in the simulation. Here we can see the Freedom KL82Z board being simulated. We can see here a keypad which we're going to set up so that we can use it together with the key scan operation and then use it for aiding the development of our complete application. In the project file key scan, I can set a breakpoint so we can get an idea of what this polling task is actually doing. That's a breakpoint being set and it's immediately being hit. And what we can see is that we read the key state and then we check for changes. What we need to know is how do we read this key state, so we're going to take a look at that next. And this is the definition of the read key inputs macro. What I've done is I read each of these individual keys and I combine the bit results into a long word so that it can be used here. If we now continue stepping, we move into the check key changes routine. Now this routine in this case will simply check for changes in the input state in comparison with the previous version. If there's no changes, nothing's going to happen. So what I'm going to do now is to set a breakpoint only when there is a change detected. So I remove this breakpoint and we let the simulation continue again. And now I'm going to press on a button. So we immediately hit this breakpoint because we've detected that at least one bit has changed between two successive polls. The bit which has changed will be detected here, and from it we will generate an event. That means that there is an event generated for every input which can change, which can be detected as being pressed, and then on a release there'll be an interrupt event generated to say that the key has been released. I also have the possibility by right mouse click to hold down multiple keys. Here we come into the routine again, and now we have 2 keys held down. I can do as many keys as I want. I can then release them by clicking on them again. If I want to release multiple keys at the same time, I just press the escape key. Now, to get an idea of the application, I've connected a virtual COM port where we're going to see the application printing out messages each time that it detects a key state change. That means each time it's informed via an interrupt event that there has been a modification. So if we let the simulation run again and we watch the terminal window, each time I press a key and release a key, then I get an event. So what we see at this point in time is that we've enabled the connections which we require for the hardware. We also have a platform where we can test the operation and then continue the application development based on this. There's one last thing that I'd like to explain, and that is, where does this keypad here actually come from? If I go back to the application hardware kinetics configuration file, here we can see it. Rather than using the standard Freedom KL82 bitmap, all that I've done is created a new bitmap which I've called Freedom KL82Z Keys. This can be simply created in Paint. Here I've taken the original board image and simply added another image of the buttons which I'd like to see. I save it and then I can reference it here. The next thing that I need to do is to tell the simulator which of the inputs these keys are connected to. To do that, I have this list called button key definitions. In this list here, I have each of the connections. I have the port which it's connected to, the bit that it's connected on, and then the location on the bitmap where a press or a click would cause the button to be detected as pressed or not. To work out these locations, I can simply hover my mouse on the button of interest. I look in the bottom left hand corner here to get the coordinates, and then I note the coordinates here of a rectangle, and then I just simply plug them into here. I do this for each of my inputs. That means that after a few minutes I've fully customized my project to allow me to work with a simulation before I ever need to have any hardware to work on. Below you can find a link to the user's guide for the keypad operation and simulation. It works in individually connected mode as shown here, and it will also work with a real matrix keypad.